last lecture we have read the partial ordered set and there are some practical applications. Now, this lecture we will see that how the partial order set can be represented pictorially and finally, that becomes a algebraic structure and we call this is Hasse diagram. So, we read Hasse diagram of poset here. So, today we will read the Hasse diagram. So, explain the Hasse diagram with some example. If we remember that we have read the directed graph of a relation. That means, a relation can be directed graph or not we call digraph. Is used to represent a relation. Now, a relation on a relation R on a set X with the property reflexive, antisymmetric and transitive is a partial ordering. And the set is X with R is called a partial ordered set or poset. Since it is finally a relation on a set X, so we can represent this thing by a digraph. Now, we take one example first. That same example if I consider that we have a set X having 4 elements, say 1, 2, 3, 4 and relation we take is the less than equal to, relation is less than equal to. Now, if we remember the digraph, so relation we remember the relation will be the pairs 1 1, 1 2, 1 3, 1 4, then 2 3, 2 4. Since it is less than 2 2 less than equal to, then 3 3, 3 4, 4 4. So, first we see that 1 1 is there since it is less than equal to, since it is equal to. So, A equal to B, 2 2 will be there, 3 3 is there, 4 4 is there. So, that means or in other way I can tell that it is since it is reflexive, it is reflexive. So, all 1 1 A are A, A are A, it holds. So, if we draw the digraph, now if for this example, if the example continued, so if I draw the digraph and this time we are giving that first thing is we know that for digraph that all elements will be a vertex, all elements will be a vertex. So, this is my 1, say this is 2, this is 3 and this is 4. Since it is reflexive, so every time there will be a loop, since it is ARA holds. I can tell that since it is reflexive, it is a partial order, so it is reflexive and it digraph has loops on every vertex. Now, if I see that it is less than equal to, now I am considering some direction either upward or the downward direction, say 1 2, 1 3, 1 4. So, I can now put one directed edge that I can put 1 2, 1 2, since 1 is less than 2, 2 is less than 3, 3 is less than 4, again 1 is less than 3, 1 is less than 4 also. So, 1 1 2 2 3 3 4 4, then 1 2 1 3 1 4. Now, what about 2? 2 less than 3, again 2 less than 4. So, this is my digraph of the poset say x less than equal to and x equal to 1 2 3 4. Now, see, since it is a poset, so always it is reflexive, always it will be a transitive. So, now we can minimize. So, Hasse diagram is some minimized digraph. So, simply I can tell that Hasse diagram is a minimized digraph representation. How we can minimize? See, since it is poset, it is always reflexive. So, what I can do? I can delete all the loops. Since it is a poset, always it is true. So, we will not show separately. Similarly, since it is a transitive, so what I can do that if it only 1 to 2 or 1 to 2 to 3, then 1 to 3 always will delete. So, delete the edge or the edges responsible for transitive property. Finally, we will delete all the arrows, we will delete all the direction or all the arrow or the direction. That means, all edges should be, that means since all edges should be undirected. So, all edges should be undirected. Now, why we can do this thing? Because we are considering only the poset, we are considering the poset and the digraph of a poset. So, poset is reflexive and transitive. So, we are not separately giving any representation for the property reflexive. That is why we delete loops. Since it is transitive, that is why we delete the edges responsible for transitive property. What does it mean? That if it is A R, say A R B, then B R C, then I will put A R C. So, A to C will delete this, we delete A to C. Since we have already A to B and B to C. So, we do not give A R C, A to C. And now, for this type of diagram, in the Hasse diagram, always we give the arrow either in upward direction or downward direction. Since we give either upward direction or downward direction, so I do not need any arrows for that. So, we delete all the arrows from here. So, in this way we can minimize. Then how we can do that thing? So, in the first step, so Hasse diagram, so we continue the same example. So, again if I quickly draw 1, 2, 3, 4, then I give 1 to 3, I give 1 to 4, then I give 2 to 4. So, what will be my, so this is my initial digraph, then what will be my step 1? We first drop all the loops. So, we drop all the loops. So, only so, this is my step 1. and I can write that step 1 is drop the loops. Now, what will be my step 2? Then all arrows for transitive or all the edges for transitive property. That means, we can drop 1 to 3, 1 to 4 and 2 to 4. So, step 2 will be one, 2, 3, 4. So, all the transitive thing we drop. So, this is my step 2. We drop all the edges representing the transitivity. Now, my final step, we drop all the arrows. This only connection so drop all the arrows or direction, all the direction, and this is my final Hasse diagram. So, this is my final step, or this is my Hasse diagram. So, how we construct the Hasse diagram of the poset x less than equal to, where x is 1, 2, 3, 4, because earlier we have shown that for this relation r less than equal to, it is a poset. So, in this way we can draw the Hasse diagram and see that this is a very minimized form and very simple form of the digraph. Okay. Now, we see for some other example. So, again that earlier we have seen that for division, so we draw the Hasse diagram for the poset. I write in this way A B, and the relation is divisibility, where A divides B. And on the set, the relation on the set R is on the set x equal to say 1, 2, 3, 4, 6, 8, 12. So, now we know the procedure for drawing the Hasse diagram. So, first we draw the digraph. Okay. Since I have 6, 8, 12, 4 or 7 nodes. Okay. We draw the digraph. I have 1, so 2, 3, so I give in this way. Six. Okay. I draw, this is 1. So, A divides B. So, 1 divides every one, 2, 3, 4, 6, 8, 12. So, there will be some initially the directed edge to 1 to every one, 1 to 2, 1 to 3, 1 to 4, 1 to 6, 1 to 8, 1 to 12. Then 2 divides 4, 6, 8, 12. So, 2 divides 4, 2 divides 6. Okay, we can give a different color, so that we can I give a different color for 2 to 4, so that it will be clearly we can understand. 2 to 6, then 2 to 8, and then 2 to 12. Then for 3 divides only 6 and 12. 3 divides 6 and 12, I give a different color. 3 divides 6 and 3 divides 12. Then 6 divides 12. Then since everyone divides, A divides A, so I have loops to every node or vertex. I have loops to every nodes. 4 I have not given, 4 is 8. Okay. So, 4 divides 8, 4 divides 12, but 8 does not divide 12, or only 8 divides 8, 12 divides 10. So, this is my digraph. Now, first thing step 1, I drop all the loops. So, if I step 1 and step 2 together if I give, then the transitive edges also we can drop. So, I write if I give again, I give 1, so I have only, I will give only 1, 2, 3, then 2 to 4, 3 to 6, 4 to 8, 6 to 12, then I have 2 to 6, I have 4 to 12. So, this time I have drop all loops and transitive edges. And transitive edges. Now, finally, we drop all the arrow diagrams. So, this becomes my final, that simply I draw 1, 2, 3, 4, 6, 8 and 12. Or I can give the nodes blue, so that it will be clear. And I have 4 to 12, I have 2 to 6. So, simply this is my Hasse diagram. Now, we have if we see that or in the last lecture we have seen that our power set is a poset. Some power set of S is a poset. Is a poset. Now, if we consider S, the set S is 3 elements, then we can draw the Hasse diagram of PS. So, draw the of power set S. So, if we remember what are the elements of the power set, see S equal to ABC, we remember the elements will be 2 to the power 3, 8, and what are those elements? The power set, it will be the empty set, that is null set, then A, then B, C, AB, BC, CA and ABC. ABC. And the relation here we have considered when it is a poset, the relation is the subset. Okay. That means we have to show PS and the poset is I can write AB such that AB or I can write A is a subset or inclusion, set inclusion. Okay. So, how we can draw? We have 8 elements and all the elements must be the vertex of the digraph. So, directly if I draw, then this will be always some upward direction we can give. So, I can draw in this way. See, I can give the empty set as the bottom. So, I write my empty set, or I write that null. I write this is my null set. So, this is my A, this is my B, this is my C. Now, A and C, so this connection, this must be my AC. Similarly, C and B, so this edge, this node must be BC. Then A and B, so this will be AB and this will be the ABC. So, these are my all subsets, and this is the simply the Hasse diagram. If I see, this will be my Hasse diagram of the poset, Hasse diagram of PS. Relation is the set inclusion and AC is equal to ABC. So, this is my poset of that thing. Now, we can define some here this see for this type of diagram always, since it is in upward or downward direction, that is why we are omitting or we are deleting the arrows or the direction. So, we can define some maximal element or the minimal element. So, see which is the bottom element, that is my minimum, and the which is my top element, that is my maximal element. So, how we can define some maximal or minimal? I can tell some maximal, and this is for my Hasse diagram, that simply I can tell there is no element B belongs to S. If we consider a element the set S, I am telling the poset is the set S with a relation R. This is my poset. Okay. So, such that there is no element B belongs to S. So, that A is less than B, or that relation holds for all A, and this is for all A. So, obviously, this gives me my top element. So, this is my top element. Similarly, the minimal element it will be that there is no B belongs to S such that B less than A. Here R I am taking less than. So, obviously, this becomes my bottom element. So, for the previous example, that my phi, the null set is my minimal element, and that ABC, the subset ABC is my maximal element. This is for the previous or for the example of the Hasse diagram of the power set S. So, if I just consider some Hasse diagram at random, say I have some this type of, say it is A, it is B, it is C. Or I can take some so here I can, the previous example we can tell that some, it is called some greatest element or greatest element or the least element. Then I can tell that for this example, say for figure 1, this is for figure 2, I can tell for figure 1 that for figure 1 that D is the least element, but there is no greatest element, but no greatest element. Maximum elements are B and C, but no greatest element. Here for figure 2, so this is for figure 1. Then for figure 2, no greatest or neither greatest nor least. I can write neither greatest nor least. But for our this type of diagram that we have seen in our power set Hasse diagram, that we can tell that if it is A, B, C, D, then A is least and D is greatest element. So, with this we finish this talk of Hasse diagram, and again next lecture we will continue this thing.